So if the imaginary number I is equal to the square root of -1, I squared will be equal to -1. I cubed will be equal to -1 times I, which is equal to -I. I to the power 4 will be equal to I minus I times I, which is equal to -I squared, which is equal to -1, which is equal to 1, and I to the power of 5 will be equal to 1 times I, which is equal to I. And you can see if I is also equal to I to the power of 5, which is equal to I to the power of 9, which is equal to I to the power of 13, etc. And the difference between each power here is 4. So each power goes up by 4, and they're equal. And the same applies for I to the power of 2 is equal to I to the power of 6, which is equal to I to the power of 10, which is equal to I to the power of 14, etc. And the difference in powers is 4 each time. And because imaginary numbers, they if you combine imaginary and real numbers, you will get a complex number. It is composed of a real part and an imaginary part, and they're written like this. And this is the real part, and this is the imaginary part. And this can be written as Z, where Z follows all complex numbers, which can be written as C, like this. And the real part, so we can write the real part of Z is equal to X, and the imaginary part of Z is equal to Y without the I at the end. So this part, if we do imaginary like this, IM Z, we will find Y, and if we do REZ, we'll find X. Let's say we have to find the value of square root of -4, and here we would get so using third rules, we would go 4 times -1, we can just separate that, and we'll get root 4 times root -1. We can separate out the values of the thirds, because of third rules, and then we can square root 4, which is 2, and we've got the -1 left. So, and then because square root of -1 is I, we'll get 2I as our value for the square root of -4. Now, if we had a quadratic like this, -4x plus 5 is equal to 0. To solve this quadratic, we could just use the quadratic formula. To solve for the value of x, and we would have -b plus minus the square root of b squared minus 4ac all over 2a. And if our values of are written like this, ax squared plus bx plus c, which is our quadratic, so we know that a is equal to 1 because there's nothing in front of the x squared, so we multiply by 1. B is equal to -4, and c is equal to 5. So if we substitute this into the formula, we will get something like this. We'll get 4 plus minus the square root of b squared, which is -4 squared, which is 16, minus 4, a, which is 1, c, which is 5, all over 2a, which is 2 times 1. And if we simplify this, we'll get 4 plus minus root -4, all over 2. And this, we can write it as 4 plus minus, and because we found that the square root of -4 is equal to 2i, which is a complex number, an imaginary number of 2. Now we can simplify this to get 2 plus minus I. So we get two solutions to our quadratic, to our value of x. So one of them will be, because 2 plus minus I, x is equal to 2 plus I and 2 minus I. And these are the two values of the complex numbers, of the roots of the equation. And they are both complex numbers. So imaginary, we can get imaginary roots from by solving this equation to find x. So we won't get real values for our x values. Say we have a complex number z squared is equal to 8 minus 6i, which is another complex number. So to solve for z, to find the value of z, we could make z in terms of x plus yi. And if we substitute this into the equation, we'll get x plus yi squared is equal to 8 minus 6i. And we can expand out the square part, and we're going to get x squared plus 2yxi minus y squared. And this is our value for z squared. And we can write it in the formula again, plus 2yxi minus y squared is equal to 8 minus 6i. And now, if we look at the real part of z squared, so if we do re z squared, we can look at all the coefficients of the non-I values. So the real part would be x squared minus y squared, which is equal to the real part of this, which would be equal to 8. And the imaginary part of z squared would be equal to the imaginary coefficient, so 2yx. So 2yx is equal to the imaginary coefficient of this side, which is equal to minus 6i. Or, I mean, if this part's I as well, we can just cancel out the i's, so the imaginary will go away. And we don't need it either way, because remember before, when we do the imaginary part here, we don't include the I from before. So we have these two equations, and now we can do basically simultaneous equations to solve for both. We can make, say, y the subject, so we'll have y is equal to minus 6 divided by 2x, which we can rearrange to get minus 3 over x is equal to y. And if we substitute in the equation above, minus y squared is equal to 8, x squared minus 3 over x all squared is equal to 8, we can get x squared minus 9 over x squared is equal to 8. And now we can rearrange this by multiplying by x squared on both sides. We'll get x to the power of 4 minus 9 is equal to 8x squared. And if we leave this all in one side, we'll get minus 8x squared minus 9 is equal to 0. And this looks very similar to a quadratic, except we have 4 and 2. But to make into a quadratic, this is basically a pseudo-quadratic. So to leave in terms of a quadratic, we can just make our x squared is equal to a. And we'll get a quadratic in terms of a. Minus 8a minus 9 is equal to 0. And now all we have to do is solve for a. Okay, how do we do that? So factorization. Two numbers that multiply to make minus 9 and add to make minus 8. Which ones would they be? So if we have a minus 9 times positive 1, 9 plus 1 is equal to 8. That's minus 8, sorry. Minus 8. And then minus 9 times 1 is equal to minus 9, which is exactly what we want. So we can just factorize this out and leave it minus 9. So leave one of these in one bracket next to the a, and the other one in the other bracket plus 1. And then we make it equal to 0. Now we can just separate each one, a minus 9 and a plus 1 is equal to 0 is equal to 0. So we'll get a is equal to 9 and a is equal to minus 1. So since we have our values for a is equal to minus 1 and a is equal to 9, we know that a is equal to x squared, so we can write x squared is equal to 9 and minus 1. And if we square root both, we'll get x is equal to plus minus 3 and the square root plus minus the square root of minus 1, which is an imaginary number, which for this case we can just ignore, because remember, x and y in the complex number form have to be both real numbers. So x has to be a real number and y is a real number. And because we have got our x and y as one of them as an imaginary, so our x is imaginary, we can just ignore it because it's not a real number, because x and y in the real numbers have to be real. They have to be real in the complex form. So we found our value for x could be plus 3 or minus 3. So now to find our value for y, we can just substitute in this equation here. Y is equal to minus 3, and then we've got plus minus 3. Now we can write this out, because the plus minus 3, we can just, and we got a minus, we can just flip it. So we got y is equal to minus plus 3. I'll go into what this means in a second, like this sign means. So 3 over 3, which is equal to 1, which is equal to y is equal to minus plus 1. So now we have two values for y, x and y. So x is equal to plus minus 3, and y is equal to minus plus 1. So this means if x is positive, so say we have x equals 3, then y has to be the negative of it. That's why it's flipped over here. So we will have to get minus 1. And if x is equal to minus 3, our value of y has to be negative of that, which is positive 1, which is equal to y. So if we substitute this into z equals x plus yi, which we defined it at the start over here, we can just substitute in the equation. So we either have 3 minus I, which is 1i, or minus 3 plus I. And these are the two possible values of z from this equation here. And that's the end of the video. Thanks for watching.